Dredging can be defined as the underwater excavation of soil or rock. Pretty simple, so getting the job done is anything but. Dredges can make sand rain from the sky, clear mud from the biggest of rivers. They can cross continents and transform underwater mountains of silt into lush wildlife habitat. Dredging can compress centuries of geologic evolution into an almost routine construction project. Dredges come in two basic types. Mechanical dredges scoop material from the water with some type of container, while hydraulic dredges act like giant vacuum cleaners, sucking a mixture of sand, rock, and water from a river, lake, or ocean bottom. Today's global economy relies on mammoth-sized vessels to move the world's cargo. Big ships need big water, and that means dredging. Big time. The basic unit of domestic and international shipping is the steel container. These 40-foot-long boxes are filled with everything from sneakers to Subarus, and then piled on top of monster-sized ships.
What we're finding is that many of the vessels that carry the commodities, oil, food, grain, these types of vessels, the economics for the shippers tells them to get larger, tells them to get deeper draft.
Draft is the depth of a ship below the water surface. Modern harbors are in a constant scramble to keep their waterways deep enough for the drafts of modern container ships.
This channel right now is at 45 feet deep, and based on the tremendous import business that the United States does, it's a lot less expensive for the products to come via larger container ships. Larger container ships means deeper draft.
In May 2005, the ports of New York and New Jersey began a joint 10-year, $1.6 billion project to deepen the main shipping channels into the harbor to 50 feet.
This particular deepening project is one of the top two civil works projects in the nation. 1/3 of the nation is touched by the commerce that comes through this port.
In the Kill-Van Kull section of the harbor, an array of dynamite charges is used to loosen the hard rock below the surface.
That fractures all of the rock into maybe football size, basketball size chunks, and then a backhoe goes in and lifts that material out.
But the largest backhoe dredge in the world, named the New York, don't need no stinking dynamite.
We're able to dig rock that other machines would need to have blasted in order for them to dig it. You see the bucket behind me, it's got the ability to cut into a sheer face of rock, and depending on the strength of that rock, actually break it as it goes along, thereby getting rid of the need to have to do the blasting.
This bucket can pick up to 26 yards, and once we got the whole load, the boom, the stick, the bucket, and the material, we're picking up like close to 260 tons every 50 seconds.
The excavator itself has got two diesel engines with a total of 3,000 horsepower. The breakout force is approximately 370,000 pounds. That means 370,000 pounds are applied to the end of the shovel in order to break up the rock.
Like right now, I'm booming down and I'm sticking in, and at the same time, you curl the bucket and you're watching your computer if you're picking up the material or not. So then you just boom up. The bucket's pretty heavy, so you just push this button and then it gives you more power to pick up.
This is where the action takes place. We have on the very end are the bucket teeth, which weigh about 80 to 100 pounds apiece. This edge of this tooth breaks into the gaps in the rock and helps shovel the rock into the back of the bucket. Those are connected to the lip by these adapters, which are also massive steel, weighing about 1,000 pounds apiece. This is where the 370,000 pounds of breakout force hits the rock.
The New York and other dredges are constantly working to counteract the forces in action under the water's surface. Without dredging, silt would fill in these waterways and make navigation impossible. Across the continent from where the New York is working, another dredge deepens the port of Oakland, California. Even though it's called the Florida, this vessel operates primarily up and down the west coast of the United States. The Florida is what's known as a cutter suction dredge. Thanks to its efficiency and versatility, this is the most commonly used type of dredge in the United States. The cutter head suction dredge has a revolving head at the business end that dislodges sand and rock from the bottom of the waterway. The cutter head revolves around a mouth that is attached to a powerful suction pump. As material is dislodged by the cutting action, it's sucked up through a pipe connected to a barge or disposal area on the water's surface. As it dredges the main shipping channel in the port of Oakland, the Florida depends on every member of its 16-person crew. But the operator known as the leverman has an especially complex task.
He's responsible for our presence in the ship channel. So he's monitoring the radio for navigation interests, and he's got to be prepared for ships to pass. From a production standpoint, he's looking at whatever the limit might be. And in some cases, the material is so tough that his limit is he's using all the cutter power he's got. Or in some cases, it might be that he's just swinging as fast as he can, and we're limited by how much ground we can cover.
You got to have a mental image picture of what your cutter is doing, and how hard it actually is cutting in the material, so you're actually mentally where the cutter is. You can feel the force that is going into the bank. You can tell by the cutter amps how much, it gives you an indication. I can feel on this joystick how much tension there is where the cutter is.
It's got 17,000 installed horsepower. It's got a 3,000 horsepower cutter head, 2,000 horsepower ladder pump, and a 10,000 horsepower main pump. It pumps through a 34-inch pipeline, so a lot of times you'll hear it called a 34-inch hydraulic dredge or a 34-inch cutter suction dredge. It's one of the largest cutter suction dredges in the nation.
The Florida's main attraction is a nasty-looking beast with interchangeable heads.
It's about 15 tons of steel. It's a 5-arm cutter head, and it's got what we have right now on it are the wide flared teeth, and these what we call the spades. As that cutter head's turning, what actually digs the material is this tooth system.
When they're on the clock, these iron monsters work 24/7 to achieve maximum productivity. The only thing that'll stop the sucking is a breakdown, like this one. The Florida's cutter head tried to bite off more rock than it could chew.
It encounters something substantial enough, as this cutter head's rotating, you can actually break the tooth system, which is what happened here, and that's the reason we took this off today.
But the work never stops, thanks to the dredge's unique power plant. The Florida is one of the only electric dredges in the nation, and draws its strength from a dedicated substation back on shore.
We bring 14,000 volts out to the dredge via submarine cable. We have about 15,000 feet of that cable.
This makes the ship of great value in urban harbors, where the pollution of massive diesel engines running around the clock would be a deal breaker. A few miles from where the Florida is working, another dredge plies the cold outer waters of the San Francisco Bay. The Essayons is what's known as a hopper suction dredge, a self-powered vessel capable of storing dredged material on board in a huge holding tank, or hopper, and then transporting it to a disposal area. Hopper dredges are the weapon of choice when dredged material needs to be transported more than a few miles, and are often used to clear offshore sandbars. The hopper dredge works by making repeated passes over the target area. Two suction pumps called drag arms are hinged on each side of the ship. The intake openings are dragged along the bottom as the vessel moves forward at speeds up to 3 miles per hour. The dredged material is sucked up the pipe and deposited in the hopper. Once full, the dredge moves to the disposal area to unload before starting the whole process again. The hopper dredge Essayons is the most technologically advanced dredge in the American fleet.
We've got all of the latest modern electronics on board here. We have automatic radar plotting aids. We have automatic vessel identification systems. We have engine room monitoring systems to control all of the engines, the RPMs, the speeds, the pitch, all controlled electronically from up here. We have electronic control of all of the functions. We'll know about watertight doors, fire safety, pumps, valves.
The sophisticated electronics do more than control the movement of the ship. The newest technology makes visible what dredge operators could only imagine for hundreds of years.
This is called the pit. This is where the dredge control officer takes care of all the dredging operations. He's controlling 2 drag arms, one on the port, one on the starboard, and he monitors the whole control situation from up here. He's got 3 screens in front of him, and he's monitoring the dredging process. This is the DTPS system, and it shows the ship going back and forth in the channel, and the different colors represent the different soundings from the survey. And as you can see, as we're going back and forth, it's turned these areas to blue, which are the deeper areas. And as they become blue, we stay away from them, and we just concentrate on bringing the ship through the yellow and the green until we turn them blue. And then when it's all done, we move on.
Smaller and faster computers have led to sophisticated instrumentation that allows dredging work to take place in a way never before possible. These modern instruments give the essayants a big advantage in the open ocean.
The north coast here, we get predominantly high northwest winds during the summer, and they'll blow 25 knots most afternoons, so you get a good swell coming in. We'll operate in swells up to 12, maybe push it up to 15 feet before we'll run off of a bar. We have swell compensators. They're these large hydraulic rams that run up and down on the deck, and what they do is when the ship is operating in a swell, she'll heave up and down on the dredge site, and the drag head is on the bottom. What the swell compensator does is that it runs up and down automatically and keeps the wires taut on the winches so that they don't spool out, and you get a bird nest on the winch, which can make a day pretty miserable.
Modern dredging has its share of challenges, but over 100 years ago, the world's biggest ever construction project almost proved too much for an army of dredges. Dredges may look prehistoric, but the guts of the modern dredge reflect some very sophisticated research and development. The Center for Dredging Studies at Texas A&M University is a landlocked facility that houses a remarkable array of equipment and monitoring devices. The Coastal Engineering Lab at the center boasts a 75 by 120-foot wave basin. The lab also includes an experimental dredging tank, complete with a custom-built cutter suction dredge unit.
It's a scale model of a real dredge with all its same functions. So here in clear water and, let's say, clean sand, you can actually see a lot more than in reality and do research how certain things behave in reality.
As the simulator's operating, it's going to be run back and forth, sweeping motion in a pit through different types of material, whether it be a clay or sand or gravel, depending upon what type of simulation that they're running their tests under.
It's of interest to know what size forces you need and how much power you need to, let's say, cut a certain amount of cubic yards per hour, certain production. And if you can get a handle on how certain things behave, you can scale that up into a real design of larger dredging equipment. Cutter suction dredges in its functions have been the same for years. Data logging, it has automated movements and state-of-the-art production monitoring and control.
Today's cutting-edge technology is the result of thousands of years of innovation and refinement. As early as 5000 BC, the ancient Egyptians tried to control the flow of the Nile River by building canals to divert annual floodwaters to distant fields. And each year, these canals had to be cleared of silt. This was one of our first organized dredging practices. Egyptian farmers used primitive hand dredges, basically cloth bags at the end of poles that were dragged along the canal bottom. But it was the Eastern Mediterranean that gave rise to the first marine dredging technology. Solid archaeological evidence indicates that the Phoenicians built artificial harbors at Sidon and Tyre in the 13th century BC, in what is now Lebanon.
Mainly it was for commerce, bringing in big clay jars full of wine and olive oil, bringing in troop movement. A lot of times it's war has to do with the dredging. You know, the bigger ships carrying all of their horses and their armor and their soldiers, the bigger their galleys got, the deeper they had to go in the harbors that they were running up a lot of these shallow rivers.
The Phoenicians were probably the first to dredge from a platform out in the water.
Basically, it was a flat-bottom barge. They would have a big tripod set up in the center of this scow, and they would have a long rod on it. On one end of it, you would have a hide bag or a cloth weave bag that they would dip down into the bottom. A couple of big guys would move the arm, it would drag across the bottom, fill up, they'd swing it up, bring it on deck, drop it, scoop it out, and take it back out.
The Roman Empire absorbed this new technology and applied its own refinements based on the availability of slave labor.
When they had their empire and they were plundering everybody, they had to get everything out of the countries, and so they had ports that weren't deep enough for their galleys to come in. In fact, the Romans were very good construction engineers. They used concrete over 2,000 years ago. They would build quays and piers.
By 400 AD, the Romans had built lighthouses from the Mediterranean all the way to the North Sea. But without systematic dredging, the harbors they protected were threatened and ultimately destroyed by siltation. Throughout the Middle Ages, European innovators made crude attempts to try to combat the relentless forces of wind and water. These included the dredging rake, operated from a riverbank by 8 men trudging in a circle. Because the Netherlands, or Low Countries, are below sea level, they had even more reason than most to advance the art of dredging. In the 16th century, Dutch engineers developed the mud mill, essentially an endless chain of digging planks driven by men and horses.
They look like a wheel that you would use with chipmunks, and as the wheel would go around, this had paddles attached to it.
And it was very labor intensive and very similar to what we do now. Very repetitive. Around and around you would go, all day, all night, until you got it down.
In the 17th century, a Frenchman named Denis Papin invented the centrifugal pump, which used a spinning motion to move a liquid from the source to the delivery point. The design allowed for the transport of large quantities of water mixed with sediment. But it wasn't until the development of steam-driven engines in the mid-19th century that dredging became a force to be reckoned with.
The steam engine was a real big technological breakthrough at the time because it got rid of the 5 horses and the feed and the sanitary problems associated with that, and allowed them to get bigger pumps. Bigger pumps mean more material.
The steam power gave them the ability to have bigger equipment, bigger buckets, and have the suction on suction dredges, and so that they could excavate more material with less energy and equipment.
In the mid-19th century, the digging of the Suez Canal marked a turning point in the history of dredging. Work began in 1854, using mostly animal and slave labor. But it wasn't until 15 years later that it was completed, thanks in large part to steam-powered bucket dredges. The completion of this 91-mile canal in 1869 shortened the sea route between Europe and the Far East by 5,000 miles. In the early 20th century, it was America's turn to shine, in a small tropical country called Panama. A route across the Central American Isthmus was first considered in the 16th century. Spanish rulers realized they could transport the riches of Asia back to Spain much more quickly if they could circumvent the South American continent. Finally, in the 19th century, the French developed what seemed like a workable plan for a crossing. After their success with the Suez Canal, the French were confident they could repeat the achievement and build a waterway through 51 miles of Panamanian jungle. But tropical disease and accidents took the lives of 25,000 people in less than 10 years. In 1904, the U.S. government bought the French company's assets for $40 million and began construction. Included in the deal were 7 bucket ladder dredges used in the first attempt. The bucket ladder dredge was the earliest form of mechanical dredge. It uses a continuous chain of buckets rotating around a rigid frame, called a ladder. When the ladder is lowered to the bottom at an angle, the empty buckets ride down and dig into the mud. The loaded buckets then return along the upper side of the ladder and dump out at the top. As work on the canal dragged on, project engineers searched for a more effective machine to combat the thick Panamanian muck. The Ellicott Machine Corporation of Baltimore, Maryland was enlisted to custom build 6 cutter suction dredges.
They got a lot of high horsepower, and the pumps could get bigger and bigger and bigger, and they started moving more and more material.
With a major assist from the Ellicott dredges, the canal was finally completed in 1914. It was the largest engineering project of its time and involved the clearing of 100 million cubic yards of dirt. The cutter suction dredge that earned its stripes in the Panama Canal hasn't changed its basic design all that much in over a century. But the scale of today's cutters makes projects that were once impossible commonplace. As sure as beads will fall on Bourbon Street during Mardi Gras, the Mississippi River will need dredging year-round. Army Corps dredges work constantly to keep the Mississippi River moving.
About 200 million tons of cargo came by this point by barge last year. In order to understand how much cargo that is, it would take a truck every 3 seconds rolling down the highway to move that material. That's a truck every 3 seconds, 24 hours a day, 7 days a week, 365 days a year.
Well, right now we are about a mile away from where La Salle planted the pole in the name of France in 1683. And since that time, this river has created huge channels of navigation for the United States.
The Mississippi River drains 41% of the territorial United States. That's a lot of area. Once it rains or ice melts on those areas, all that water is going to go through the Mississippi River. It carries a lot of water, plus also a lot of sediment.
The Eagle One is a hopper dredge. Like other hopper dredges, it's self-powered and deposits its dredged material in a disposal area.
The hopper dredge is an excellent choice for this type of work because it's in a very busy channel, and a stationary dredge would have difficulty with the traffic in the river. A hopper dredge is maneuverable, it can avoid the other traffic.
Right now we're dredging, and this is the slurry that's coming in from the 2 main pumps that we pump it up. What we do is we suck up the material from the drag arms that went over on the side. It goes through the pumps and it comes down these chutes into the hopper.
On a good day, the Eagle One can clear 5,000 dump truck loads worth of material from the river. If the drag heads get into thick sediment and sufficient power isn't applied to keep the ship moving forward, the powerful river current will snap the drag arm guide wires, a very costly accident. It's this type of risk that demands a highly skilled operator to man the controls.
The winches work at a certain speed, so I've been doing this since about '84. So I know that speed right there is about 2 feet. That's 6 inches. So without looking, I got a pretty good idea how much I just came up.
The Eagle One toils round the clock at work that's never finished, but that started over 100 years ago.
Dredging in the river was not really accomplished until about 1882. Up until that time, the channels were blocked by the natural sandbars, and the draft across those bars was about 12 feet of water.
But recurrent flooding decimated surrounding land areas. The Great Flood of 1927 covered 23,000 square miles and forced 700,000 people from their homes. Soon after this catastrophic event, Congress passed the 1928 Flood Control Act, which gave responsibility for maintaining the river to the U.S. Army Corps of Engineers. In the decades that followed, the Corps spent billions of dollars on year-round dredging to control flooding and assist ship traffic through this critical waterway.
It's an ongoing process. Every year, the rains and snow melt up north, and it washes all the siltation down to the river here. And dredges like ourselves have to come in and suck up that material that's shoaled back in to get it back to 51 feet so the ships can come in.
When the Eagle One has filled up the hopper, it heads out to an open water disposal site. The Eagle One has a nifty design feature known as a split hull. The ship is able to mechanically separate into two sections, allowing all that silt to sink safely to the ocean bottom. A few miles upriver, the dredge Jadwin gets down and dirty. Less shipping traffic and a more silty bottom in this section of the river call for a different type of machine. The Jadwin is a dustpan dredge, named for the shape of its suction head. Dustpan dredges were designed for the Mississippi River and first built by the Army Corps of Engineers to fill the need for a dredge that could operate in shallow water and still be large enough to quickly excavate the shipping channels. The Jadwin is positioned in the channel using two large anchors that are sunk into the bottom, about a half-mile above where the dredge will be working. Cables running from the anchors back to the dredge are used to drag the dredge forward, while its powerful pumps are working to suck up the debris.
This is where it all happens. This is the business end of the dredge, the dustpan that actually scoops up the material off the bottom of the river. We inject the water into the sand with this high-pressure water jet. Have you ever taken a water hose and squirted it straight down into the soil? Well, that's essentially what these water jets are doing down on the river bottom. They are fluidizing that sand so that it can be sucked up by the dredge pump.
The slurry dumps into a holding tank before being pumped out. When maintenance work happens here, everyone on board holds his breath.
This part of the dredge up here is the most dangerous part of the dredge, we think. If you fall in right here, you don't have a very good chance of getting out without going all the way through the dredge and through the propellers in the back. So we put these safety ropes here. We call them the Jesus ropes. If you fall in the water and you miss that rope, Jesus is the only thing that can save you.
A pipeline carries the slurry several hundred yards away from the shipping channel.
We're at the end of the pipeline where the material comes out of the pipe and goes into the river. When the material exits the pipe, it strikes a baffle plate, and we can change the angle of this baffle plate and actually steer the pipeline up the river, and so that we can discharge this material where we want it to go.
In the past, Mississippi muck was dumped wherever it was easiest and cheapest. But in the 1990s, state and federal agencies realized that they were wasting a valuable natural resource. Since underwater silt and sediment are often the final resting place for toxic waste that is washed down from industrial sites, modern dredging can have dire consequences if the right precautions are not taken. The massive deepening project in the New York-New Jersey harbor impacts several areas that contain toxic materials. For decades, industrial waste trickled down the Hudson River and its tributaries, creating a dangerous layer of contaminated sediment in some parts of the New York-New Jersey port.
This New York Harbor, New York area, of course, was very heavily industrialized in the turn of the century. And we're dealing with that industrial legacy right now.
Being the top layer of silt sediment material in the bay, and being that this is a very industrialized and urbanized bay, this top layer does have contamination in it.
While the backhoe dredge does a superb job grinding out the hard rock sections of the New York-New Jersey port, other areas of the harbor call for a more delicate approach. Specialized equipment must be used to ensure the dredge operations don't release toxins back into the environment. The Michigan is what's known as a clamshell dredge. This clamshell bucket has been modified into what's known as an environmental bucket, designed specifically for handling light sediment and utilizing special rubber seals to keep spillage to a minimum. As the bucket is raised, its speed is also controlled to reduce the amount of overflow.
Candidly, dredging, although it's a technological challenge, is actually the easier part of a program. The most important program is where is it that we take the dredge material and what it is we remediate, and will it be acceptable?
One of the ways to render the hazardous material into a form that can be used safely is to mix the sediment with Portland cement. Portland cement is a compound that not only hardens when mixed with water, but also becomes water resistant.
In the treatment process with the cement binds the sediment particles together, and in that process entraps any contaminated material. It's typically heavy metals, binds that within the cement so it doesn't leach.
The mixture will remain stable over time and can be used to cover or cap land that may still contain toxic elements.
In this area, we're taking it to a couple of different sites. We have some park area that is being capped. They were industrial sites, industrial landfills, and they're being capped and are going to be made into a park.
The beneficial use of dredged materials also includes the rebuilding of areas lost to development and erosion. On the west coast of the U.S., the California State Conservancy has implemented a 50-year plan in conjunction with the Army Corps of Engineers to restore wetlands around the San Francisco Bay.
Most of the projects started in the 80s or the 90s, and they were relatively small, 50 acres here, maybe a couple hundred acres there. And now we've gone from that to one of the last major projects we did, Sonoma Baylands project, was 300 and some odd acres. And that was with the deepening of the Port of Oakland to 42 feet, a decade ago. And now this decade, we're deepening the Port of Oakland more, and we're doing a really truly landscape scale project. Hamilton Wetlands Restoration Project is currently 1,000 acres, and we're trying to expand that to 2,600.
It'll take about 20 years of maintenance dredging in the San Francisco Bay to amass the 25 million cubic yards needed to restore the Hamilton wetlands in San Pablo Bay, north of San Francisco.
You pump it in there, and then it comes out the end of a pipe, and by managing how you decant the water off the top, you make the material flow around to get the line and the grade you want.
Dredged material is also being used to restore ocean beaches. Beachfront construction and breakwaters have drastically altered wave patterns. This has led in turn to disastrous erosion on many sections of coastline.
In a situation where you don't have the sediments and you just have a seawall, large waves come in unabated, attack the seawall, and cause all that energy turns into turbulence in the nearshore zone and causes greater acceleration of the erosion. And so seawalls, although they do serve their purpose in the immediate region where they're put in, eventually we'll have nothing but an armored coastline.
The Army Corps has placed dredged sand several hundred yards offshore the Ocean Beach area south of San Francisco, with the hope that natural tidal and wave action will deposit the sand back onto eroded beaches.
After they come into the nearshore area, they will bottom dump the sediments into a berm, which is parallel to the shore face. We hope to get about 1,000-foot long berm, maybe about 3 to 4 to 5 feet high, a couple hundred feet wide. And then the action of the waves will push that sand into the nearshore zone where it will widen the beach. And then it'll provide sediments when storms attack the coastline to form offshore sandbars and dissipate the wave energy through breaking.
Dredging contributes to land restoration, but the modern generation of dredges can also create brand new land. Mega-sized ports are the way of the future. In the Los Angeles harbor, the Pier 400 project created a 600-acre terminal for shipping containers, the largest such facility in the world. The job involved a unique partnership between the Army Corps of Engineers and the Port of Los Angeles.
The Port of LA's interest was to develop a harbor for commerce and to deepen it to 81 feet. Their objective met our objectives in that we needed a place to put our dredge material and they needed to have a landfill. So it worked out perfectly.
5 dredges, led by the workhorse Florida, were contracted by the Army Corps to deepen the main channel to between 53 and 81 feet, deep enough to accommodate any ship in the world today. The massive scope of the work, combined with the heavy traffic flow in the harbor, gave the Army Corps a nearly constant headache.
You have about 3 to 5 miles of dredge pipe at times to deal with in an active harbor, one of the more active harbors in the world. We could not impede traffic at all, and maintain safety was a critical aspect of this job. So having to deal with floating pipe and then submerged pipe, moving it on a regular basis, was very challenging.
To solve some of those challenges, the Army Corps turned to its Engineering Research and Development Center in Vicksburg, Mississippi. The ERDC occupies 1.7 million square feet and includes an acre-sized simulation tank in which a 44,000 square foot model of the Los Angeles harbor was built. Experiments tested tidal action and the effect of wave energy on siltation in the harbor. It took 6 years of non-stop dredging to create a 500-foot wide channel that extended 3 miles out from the harbor into the open ocean. The Florida and other dredges scooped 60 million cubic yards of material from the ocean bottom and piped them onto a landfill, on top of which the new container facility was built. A small army of dredges is bringing the United States into the 21st century, well equipped to compete in the global market. But thousands of miles away, an armada of new dredges bigger than any ever built are transforming the map of our world. The growing population and superheated economies of the Far East make land a very precious commodity. The demand for real estate is fierce, especially near the ocean. The Hong Kong airport recently opened to air traffic on 2,300 acres of land that didn't exist 10 years ago. 250 million cubic yards of sand and clay were pulled from the ocean floor to complete the project. In Malaysia, hundreds of yards of new property are being added to the shoreline each week.
They had to have the big hopper dredges. They would come in and go offshore of Indonesia and Malaysia and dredge up the sand, maybe do a 100 kilometers round trip to get the sand, bring it back to the harbor, and either spray it ashore or pump it ashore and build the new land.
In the Philippines, state-of-the-art dredging helped build an underwater natural gas facility 35 miles off the coast of Palawan Island. A foundation of dredged sand and gravel was poured nearly 1/2 mile below sea level, and then a massive concrete structure was positioned on top. When fully operational, the plant will be able to fill the energy needs of the entire nation of the Philippines. Material used in the creation of new land must be fine-grained and dense enough to support the enormous weight of new construction. As the demand for new land increases, dredges have to venture further and further out into the ocean to find construction-quality sand. To make these trips profitable, dredges have to get faster and bigger, much bigger. When it was launched in the year 2000, the Vasco da Gama was the largest hopper suction dredge ever built. It weighs 60,000 tons and is more than 200 yards long. The drag arms weigh 55 tons each, and it only takes about an hour to fill the hoppers with 35,000 cubic yards of ocean bottom. The Vasco da Gama has 8 separate hoppers, and the operator must carefully control how these are filled. Loading too much sand too quickly onto one side of the vessel could cause the ship to capsize. Once the gargantuan hoppers are full, 2 20,000 horsepower engines can power the Vasco da Gama back to port at nearly 15 miles per hour. Its sandy treasure is offloaded in one of 3 ways: through a pipeline up to 5 miles long, through the bottom doors, which only takes 15 minutes. Or it's rainbow, a process that shoots the slurry through the air into an arc of more than 100 yards. With the awesome capabilities of the modern dredge, it was probably only a matter of time before we came up with some mind-boggling new applications. In the Persian Gulf, the world's largest land reclamation project is underway. In a venture authorized by the royal family of Dubai, 3 islands in the shape of palm fronds are being built a half-mile offshore. 12,000 private homes, alongside 100 luxury hotels and restaurants, will adorn these new islands, which average about 16 square miles each.
In order to do that, they are having to bring in large quantities of sand to build these islands, or the palm islands, which are essentially arranged like palm branches on a palm tree. And so this creates a large area of beach because you've got beaches on both sides of the palm leaves, if you will. The dredges that are being used to bring in that sand are very large, hauling on the order of 30 to 40,000 cubic yards at a time.
It's huge. It's a 10-year construction project for reclamation and to build this whole fantasy world that they want over there, to bring in restaurants and tourists and rich people that want beachfront property condominiums.
And the 3 islands are just phase 1.
They're building islands in certain shapes. Out in the Gulf there, it looks more like a resort area, but it has a certain shape that you can recognize from up in the air.
Joining the Palm Islands, Dubai, is a group of 300 artificial islets. Tiny islands that, when viewed from above, will look like a map of the world. Dozens of these private islands have already been sold at prices ranging upwards of $10 million each. When complete, this undertaking will have cost over $14 billion and will have created some 450 miles of brand new coastline in the Persian Gulf. Such is the awesome power of dredging. Down and dirty machines that create as easily as they destroy. Today's dredges are able to do in months what may have taken nature thousands of years. 24 hours of every single day, dredging helps drive the global economy as it transforms our planet.
What was once cutting-edge technology